J I is what we will call a flux vector, right, in coordinate notation. Okay, and for coordinate notation, I equals 1, 2, 3. For our purposes, this is just a way to specify explicitly the components of a vector in 3 dimensions. Okay, if we were doing a class in continuum physics, we were doing lectures in continuum physics, this would be set up much more carefully than that, right? But for our purposes, it just denotes the components of a vector, right? And when we explicitly refer to the components of a vector, that sort of notation is called coordinate notation. All right, so then what we're saying is that J, if we wanted to write the vector in so-called direct notation, okay, J is just the collection J1, J2, J3. Okay, and this is what we call direct notation. Okay, properly, the left-hand side of this last equation, J equals J1, J2, J3, is direct notation for the same vector. Okay, so we will often switch back and forth between these two notations, though for what we need to develop, we are going to use coordinate notation a little more than direct notation. Okay? But they are essentially just different ways of describing the same thing. Since J is a vector, there is also a way of describing that J is a vector to simply say that J, being a 3-dimensional vector, J belongs to R3. Okay, that's just notation, right? All this means is that J is a 3D vector. Okay, you note that exactly the same thing can be said for X as well, right? So likewise, we have X equals X1, X2, X3 arranged together as a vector, right? And X belongs to R3, and this thing has more meaning because not only is X a vector, a 3-dimensional vector, but X also is a point in 3-dimensional space, right? So this has even more meaning here, really, more physical meaning. Okay, that's what we have. Now, let me see, what else do we need to state here? Okay, in order to say more about this, it's actually useful to go to a particular physical problem that this PDE could represent. Okay, so in order to see more about this, let's consider heat conduction. Heat conduction at steady state. Right, in 3D, right? Let's suppose that this is the problem we are talking about. One thing you recall, of course, that steady state simply means that there is no time dependence, right? So the time dependence has been dropped from this description of heat conduction. Okay, so if this is the case, what is U? What does U represent in the problem of heat conduction? Can you recall from your study of heat conduction previously? Right, it's the temperature, right? Okay. J then is, right, the heat flux vector. Right, which is essentially the amount of heat crossing perpendicular to a unit area per unit time. Okay, that is J, right? Now, when we have the constitutive relation J I equals minus kappa I J U comma J. Okay, this represents for us now, it essentially tells us that the heat flux vector is driven by the temperature gradient, right? So U comma J, you recall, of course, is just partial of U with respect to xj, right? So it's the temperature gradient. This constitutive law goes by the name of the Fourier law of heat conduction. Okay. Now, here, well, let me just state this here. So this is the temperature gradient, temp as short for temperature. Okay. Do you remember what kappa ij represents here? What is it called? Right. In general, it's called the conductivity tensor, right, or the heat conductivity. Conductivity tensor. Okay. Right. This a tensor can be thought about it again in our setting for the purposes we need here. It can be thought of as a generalization of a vector, and with the provision of a basis that we have, what we find is kappa ij can be, well, that's not really right. With the use of a basis that we have here, we can also write the heat conductivity tensor using direct notation. It would be kappa, right, also with an under bar. And like I said, by context, we will understand whether something is a vector or a tensor. Here it's a tensor. Why do we know it's a tensor? Because of the way it acts in this equation. Okay, so kappa is direct notation for the heat conductivity tensor. And just as we could represent the direct notation for a vector in terms of its components or related to coordinate notation, kappa can be written with the use of a basis, which we have, as a matrix, right? And that matrix consists of the components kappa 1, 1, kappa 1, 2, kappa 1, 3, kappa 2, 1, kappa 2, 2, kappa 2, 3, kappa 3, 1, kappa 3, 2, kappa 3, 3. Okay. Now, it turns out that this tensor kappa is symmetric, and there are reasons for it to be symmetric. So we will consider kappa to be symmetric, which we write as kappa equals kappa transpose. Right. So this means that in general, the 1, 2 component is the 2, 1, 1, 3 is equal to 3, 1, and 2, 3 equals 3, 2, right? Which is also written in coordinate notation as kappa ij equals kappa ji. All right. Kappa has another property which is important for the physics of heat conduction. Okay. So not only is it symmetric, right, it is also what we call positive semi-definite. Okay, and what this means is that if C belonging to R3 is a vector, right, then if we construct the following quadratic product, right, we allow kappa to act on C, right, and the product of kappa acting on C gives us back a vector, right, just like if you know, you've all probably experienced linear algebra, a matrix acting on a vector gives you back a vector, right? So that's what's happening here. Right? So kappa C is a vector. If we dot that vector with C, okay, so C dot kappa C is greater than or equal to 0, right, for all C, right, for any C, right? Well, actually, I realize I don't really need to say for all C here. All right, so if C is a vector, C dot kappa C is greater than or equal to 0. Okay. What this means is that there are actually some directions, right, for which we are allowing the possibility that there is no conduction of heat in certain directions, right? So we're allowing the possibility that for some C, right, for some vector C, this thing could be 0. All right. Okay. So and the fact that we're allowing the possibility for this quadratic product to equal 0 is what makes it semi-definite, right, in terms of nomenclature. All right. Do you recall what we are allowing the possibility for by including that product being equal to 0? What physical possibility are we allowing? It allows the possibility that for some direction C, this material actually acts as an insulator, right, that there is no conduction in some direction, right? So this basically corresponds to if C dot kappa C equals 0. Importantly, this has to be equal to 0 for C itself not equal to the 0 vector, right? Of course, if C is a 0 vector, then that's a trivial result, right? But if there exists some direction C, not the 0 vector, for which this quadratic product is itself equal to 0, then there is no conduction, no heat conduction, along C, right, in that direction. Okay. The very last, well, actually there's more, not the very last thing, but there's one more thing I wanted to say here. When we go back and look at this law here, this is, of course, the Fourier law of heat conduction. What it tells us is that the heat flux vector is directed along the negative temperature gradient, right? So heat tends to flow from high temperature to low temperature, provided we also have this property of C being positive semi-definite. Okay? So let me state that as well. Heat flows down a temperature gradient. Right, that's what the Fourier law of heat conduction tells us, with the additional condition that C is positive semi-definite. All right, the last thing we need to state here to wrap up our introduction to this strong form of the problem is the boundary conditions, right? So when we return to the boundary conditions, the first one is fairly straightforward. When we have u equals ug on the Dirichlet boundary, this is simply a temperature boundary condition, right? So in the context of our continuum potato, right, we have our basis here, the continuum potato here, the region of interest, omega. Let's suppose that the maze part of the boundary is the Dirichlet boundary, right, the temperature boundary. What we're saying is that on this part of the boundary, we have we're controlling the temperature, right? We're setting the temperature to be ug. Ug, of course, could be a field, right? That's important here. So what we're saying here is that this could be a non-uniform field, right? So that's possible. Okay, that's allowed. And then for the second part of the boundary, this condition can be written as, we are writing it as, let me see how I wrote it actually. I probably, sorry, let me just scroll back here. Okay, I did it right. Okay. This part of the boundary, when we wrote it in direct notation, I think we wrote it as minus j dot n equals j sub n. Okay. What the n there is doing is that it is the unit outward normal to the boundary. Okay, it's a field, right? It's a vector field, right? That's what n is. So when we look at minus j dot n, what we're saying is that given the fact that n is a unit outward normal, what we're saying is that we are controlling the heat influx. Boundary condition. Okay? All right. Because n is the unit outward normal, j dot n would be the outward heat flux, and the minus sign essentially makes sure that it converts that into a heat influx. We're saying we're controlling the amount of heat flowing over the complement to the Dirichlet boundary, or over the Neumann boundary, right? So over the blue part of the continuum potato, we are controlling the heat flux, the heat influx, right? So we're controlling, if that is the heat influx, we're controlling the amount we're getting there, right? Okay, so we note that we're not controlling the vector itself, right? We cannot control the vector. That the theory of PDEs tells us that. In fact, physics also tells us that we cannot control the entire vector, right? What we can control is just the normal component of the heat flux vector here. Okay. I should also write this in coordinate notation. In coordinate notation, it is just the dot product, right? So it is minus ji ni equals jn, j sub n, right? And this is coordinate notation. Okay, I believe that completes our basic introduction to the to the strong form. We will end this segment here.